Okay, so now we have this graph of our vertical position versus the time while being thrown. So this is in the hand. And what we want to do is model this motion, which we don't necessarily expect to be a perfect quadratic, say constant acceleration. There's no reason to expect that when somebody throws a ball that it would have a constant acceleration. So what I can do to fit this complex motion is double click on it. I can go to Customize and then Series. And if I scroll down to Series, this is where we found our error bars, right? So I can add my error bars, and again, I had that set to a constant at 0.01 meters. If I want to put data labels, it'll label each value. That's something that we really don't need. And then here is what I'm looking for, a trend line. The trend line is what we're looking for. The default trend line is linear. This is certainly not linear motion. We have exponential, polynomial, logarithmic, power series, all these different things we can look at. We're mainly going to do either linear or polynomial, sometimes exponential in this course. But for this, a polynomial is a reasonable fit because we're just trying to get a function that models the motion. And it's reasonable to think that that would all be factors, powers of time, having to do with the different accelerations that there are as a function of time. So a polynomial is fine. The lowest order polynomial is a second degree polynomial that it could fit to, because below that you'd have a line. So you can see here that we actually don't have perfect fit or really great fit with this motion. So a second degree polynomial, it is, we can see that, okay, we don't actually have exactly a uniform acceleration. And in fact, it kind of looks like, it sort of does this jump and that the acceleration gets steeper near the end. And so that would matter when we're analyzing the motion. So maybe if we try, say, a third degree polynomial, well, wow, this fits pretty nice. It fits this portion nicer. It misses that point a little. But here's the problem, and here's the problem when you think about physically interpreting your fits. This was the motion when it was starting from rest and just starting to move upward. Notice how this fit line for a third degree polynomial has a slope at t equals 0 that is not 0. And that's a problem because that means that it's not really matching what we know about our motion. So you can't just pick the best fit that you have with the lowest order polynomial. You have to also make sure that it matches what we are sure about, which is that I did this from t equals 0 on the beginning of the upward motion so that the vertical velocity started near 0. So that third degree polynomial does not actually work well for us, which brings us then to a fourth degree polynomial. We can see that the initial slope is actually very close to 0. And so that then it brings the ball up and then starts to give it a larger acceleration here at the very end. And this one actually covers and fits our data quite well. So you'll want to use the fourth degree polynomial fit. And again, that can be found under the data series in the Customize series. And it's where you found your error bars. You can click or unclick the trend line. And so you go to Polynomial, fourth degree polynomial. I'm going to make the line fit a different color, just again for good measure on that, because it's good to separate out what is a true curve fit versus just a guide to the eye. Now, let's say you want the equation for that fit, and you do. Then all you're going to do is here, where it talks about label, instead of saying none or custom, you're going to click this, use equation. And if I click that button, then it would display the equation on the graph. And so that's going to be what you do, so that you will upload that graph with the equation displayed on it.